All right, let's make a start. So this one's going to cover rates of change. We've done that in a previous class before, but this is this class's version of doing rates of change. So basically we're going to be covering from 16a up through to 16d. Practically the first three sections of the chapter are going to essentially all amount to just doing rise over run. That's fundamentally what the bulk of what's going on is going to be. And then when you hit the final chapter there of 16d, you'll start doing what's referred to as differentiation by first principles. That's where you're trying to, instead of find the average gradient over a particular interval, you're trying to find the instantaneous gradient, the gradient at a specific point. Before we can dive into specifically what's going on there, it's worth covering at least a few of the basic fundamentals of kinematics. So this is a study of essentially motion of a particular object. Typically, math methods will refer to things as particles. So one of the things that's worth covering is this idea of distance versus position. So although this is a distance graph that we're seeing here, when your distance is referred to as based on some fixed point, what you have is typically referred to as position instead, which is simply just where you started and where you ended, the difference between those two spots. So for instance, if I were to like run around an oval, for instance, there's 1 kilometer of oval there. If I run the entire length around, I'm starting and finishing in the same spot. My position, or sometimes referred to as displacement in physics type stuff, is going to be 0. Whereas distance covers everything that we actually did to travel that entire distance. So your distance is going to be 1 kilometer, whereas your position or displacement is going to be 0. When you have a distance graph, even though it says distance, it only ever really works if it's with respect to some initial fixed point called the origin. So even though this says distance, you have to take these things as positions, right? So the line that you have here is not like a line where if you measure the length of this line, you get the distance traveled. It's whatever y value you have is the distance from that point to the origin. So for instance, at time equals 3, you are 10 meters away from the origin. At time equals 7, you are still 10 meters away from the origin. You haven't actually moved in this section at all. Clear enough the differences between distance and position there? That's one of the tougher things to clarify there. Cool. Okay, so that's about distance, displacement, position, that sort of thing. One of the other things they try to get you to do is interpret what's going on. And we've kind of done a bit of interpreting already, just based on the fact that we're describing what was happening in the picture. Like for instance, this flat bit here is implying that no distance has actually elapsed. The particle has not gotten any further from where it started. As far as interpreting what's going on, there's pretty much only a few things you need to touch on for each stage of the journey. You want to touch on where it started, where it ended. You want to talk about the time it took to get there. And if possible, you want to talk about the speed or the acceleration. Typically, you just refer to speed for that one. And you want to do that for separate sections of the journey. And you're able to tell what those will be, right? It'll be very discrete, sharp cutoffs of each stage of the journey. Like for instance, from 0 to 3 is one section, from 3 to 7 is another section, from 7 to 20, another section again. You're just going to repeat that 3 times for the 3 separate sections. So if I were to describe section 1, I would say that my particle starts 5 meters away from the origin, and then over a duration of 3 seconds, or whatever the unit is, what is this? Oh, minutes. So over a duration of 3 minutes, it travels an additional 5 meters away from the origin. because this is a straight line, I can actually talk about its speed. Because the slope is consistent, it means the speed is consistent. The slope of any distance time graph is always the speed of that duration. Sorry, of that section of the graph, because you have distance divided by time. Distance divided by time is always speed. And so you can actually calculate what this speed's going to be. You have a rise of 5, because it goes from 5 to 10, and then you have a run of 3. So your speed is 5 over 3. Speed of 5 over 3 meters per minute. That's the first section. So we talked about the speed, it did it. We talked about the duration it took, and we talked about how far it actually got. Fair enough on the key points you have to hit there. The order of them also doesn't really matter too much. Like, don't feel like you have to hit distance first, duration second, then speed last, right? Just think about however you would say it. Make sure as long as you can hit those 3 points in some order that doesn't feel like you're jumbling up your words. As long as you can get them down, that's all you care about. Like this one here. For the next journey, for the next from 3 minutes to 7 minutes, you would just say the particle remains stationary. So that is time duration that was part of there. But saying that it was stationary actually hits twice. Stationary means it's not moving. So that's both positional information in the sense that you can just refer to what happened earlier to know that you're staying at that position. And it's also speed information because it's telling you that it's stationary. It's not going anywhere. So you could even be a bit more, you can be more efficient with the word usage as well, depending on the scenario. Then from here, you could say something to the effect of, for the next 13 minutes, so you don't even have to mention the values, you can just say how long the duration was. For the next 13 minutes, we could say the particle slowly returned back to the origin at a constantly decreasing speed. The reason why I say a decreasing speed is because you can see the slope is getting flatter and flatter. All right, it used to be fast going down. Now it's slower and slower and slower until it eventually plateaus there. We can't really calculate what this rate of decrease is unless we make a few assumptions. All right, like we can assume this is a quadratic with a turning point here. We're not really supposed to get into that much detail for this thing. So the short of it is essentially calculate speed stuff for straight lines, or if you have equations, if you have the equations, then by all means go ahead and do that. But the bulk of it's just going to be work on your straight line stuff for speed, and then everything else is what it is. Any questions as to how to interpret those graphs? That's probably the only key thing that's new enough to this area of study. Cool. All right, so the rest of this is essentially just talking about basics of rates of change. I think one key example to talk about would be this one up here, which isn't really something that's ever really assessed so much, but more so just gets the idea across. The idea is that water is poured in at a steady rate, so the rate at which water is being poured in is constant. The tap is set to a specific speed. And the graphs that are being drawn here are graphs of the height of the water with respect to the base of the jar. So you can imagine that the height at which the water rises will be faster or slower depending on how wide the base is. Right, like if I just ran the tap outside, it's not going to suddenly be several meters of water that I'm raising up to because it's got so much surface to cover. Whereas if I have a tiny little neck here, it's going to fill up. It's going to flow up real quick, right? It's going to fill up. And so basically what we're seeing here is as the width of these jars changes, so too does the steepness of the graph over those sections. And so, this one's going to be pretty constant. This one has constantly flat walls both sides, which is why we have a constant rate of change of the height. However, when we hit the neck, it gets much thinner, so the water shoots up a lot faster. There's less surface area to cover. That's what this sharp increase is. Then from here, you have walls that are either side that are getting thinner and thinner, which is why we have a smoothly increasing slope up until it becomes straight again, in which case it starts being a tangent straight line off of that point. And then just different variants of that. So that's just illustrating the concept of how, even though you have a constant rate of flow, it depends on what the question's actually asking as to whether or not your graph will look constant. So these were constant speeds, constant rates of change. Depending on what the graph is actually depicting, your thing may or may not look constant, at least not over the full duration. That's really it. That's all this one ever is, just talking about that sort of stuff. Everything else is going to be rise over run. So again, constant rate of change. What you're essentially doing is either assuming that your start and end point will be consistent across. In the case of like all of these, you have a straight line and you want to find the slope of that straight line. Or in the case of the next one, you'll have a wobbly journey, but you want to find the average across that journey, in which case you would do like the point A, the point C, and you would do your rise or run equation for that. In both cases, you're still finding the rate of change. In this case, because the journey was a straight line journey anyway, you're finding the actual speed of the journey. Again, we have distance and we have time. So if the entire journey is a flat line, then when you do your rise over run, you are finding the exact speed for the journey. Whereas when you have this wobbly thing, you're now finding the average over the journey. Because even though it's going through peaks and troughs and whatevers, when you draw your straight line connecting those 2 points and you find the slope of that, you can see there might be some parts of the journey which have that exact same slope. But the point is to essentially smooth out that slope and figure out what is the average slope across that journey. That's what that one gives you, which is why we have a different term for it. That is the average rate of change, or in most cases, the average speed, because speed typically is rate of change. Fair enough so far? Is there any questions? All right. Last thing to cover will be probably the tougher topic, which is how to do differentiation by first principles. Or at the very least, it'll be more lengthy. Because that's what we do in 16D, which is instantaneous rate of change. We have this wobbly journey, but instead of trying to average out across the entire journey, we want to figure out what is my speed at this specific time, or this specific time. That's what your what your speedometer would tell you. You look at the car, you see what speed you're currently going. You don't really want to know your average. You want to know what speed you're currently going now, so you don't get a ticket. But okay, so we talked about average already. What differentiation by first principles is repurposing your average rate of change equation, or, rise over run, as you'd more commonly know it. So we could take the average rate of change from 0 to 2, and that would give us some slope. Right? In this case, we get the slope of 2 if we use those particular points. But if I want to know the specific slope at x equals 2, we can see the slope of this line is not really the same as the slope here. It's close-ish, but not a great estimate. If I instead did a point here and a point here, and drew the straight line across those 2 points, that would be a lot closer. Still not perfect. That's essentially what's happening with differentiation by first principles. We are slowly and slowly decreasing the width of the difference between those 2 points. So if I want to find, I'm using a cubic here because the numbers are a bit bigger. You can see the change in a bit more detail. So we have this cubic, and we want to find the rate of change specifically at x equals 10. From there, one thing you could do is do one value either side. You could do the average rate of change from 9 to 11. That's going to get you 301. If you want to be even more accurate, you do less decimal places, 0.9 and 0.1. So now you're doing Yeah, 0.1 as a gap rather than 1 as a gap. Do your equation once again. Oh, 300.01. That's pretty cool. We can actually see a pattern here. This is essentially getting closer and closer to 300. And so what we essentially say is that the rate of change at x equals 10 is going to be 300. That's more of like an eyeballing it approach. There is a mathematical equation behind it, but this is more so just the concept through which it was birthed. So the way that we repurpose this a little bit is instead of doing x2 take x1, we're just going to call that a thing called delta x, because that's the thing that we're trying to modify. We're trying to make that go as small as physically possible. So we want to call that its own single variable. That way we can modify it a bit easier. From there, basically, instead of having y2 and y1 up here, you can now rearrange what those are going to be like. So I guess I should say f of x2 and f of x1, which are technically y2 and y1. You can use this new equation to rearrange these to get your equation purely in terms of delta x and a single x coordinate. The book will use h typically, but it's just a letter at the end of the day. What we do from there is we stick a limit on the entire thing, and we say what happens as delta x, that gap between the points, gets infinitely close to 0, becomes essentially the same point. When you do that, your 2 points are overlapping. The slope at which you take is now equivalent to the slope of the line at that point. It's actually identical, not with a slight error attached to it. This does require at least a basic understanding of what's happening with limits. I think it'll be fairly obvious what happens just by looking at an example. So I won't spend too much time on like a limit theory. But is at least fair enough the concept as to what's going on? This idea of shrinking that gap, making it more accurate. Okay, that's good. All right, so how do we actually do this? Well, we need an equation and we need a point. This point, we typically only really need the x value. We don't actually care so much about the y value, at least as far as this equation is concerned. You may not actually get the value of the x, but you might just be given the fact that it is an x instead of just like x equals 10 specifically. But in most cases, you've got the actual value. From there, we sub into this equation. So we have our f of x, we have our x, so we just replace everything with what we need to. Every x in this equation gets replaced with 10. So there's the 10, there's the 10. And delta x we just leave. Delta x is what it is. F of x, obviously, just f of 10. But because we know f of x is x cubed, instead of putting f's at the front of these, we put cubes on them all. And that's basically all that's going on. The way we work with limits, at least in the context of differentiation by first principles, is you start by expanding out the numerator. If you expand that all the way out, and then simplify, 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 you'll get to a stage where the constants will disappear. Plus 1,000, minus 1,000. Those will delete themselves. What you'll see is that you have a stage where delta x, or in some cases you'll write h, delta x is in the top and bottom. You can now cancel it out as a common factor. From there, literally all we're doing is subbing in delta x equals 0. So you plug in delta x equals 0 into both of those spots, and what you're left with is the 300 that we were expecting. That's all you do for limits. There's a whole bunch of theory around it, but fundamentally it's just expand your numerator, delete the denominator, and then sub in whatever this number is pointing to, which for this purpose is going to always be 0. That's all you need to know for limits for this one. Make enough sense? Anything to dive into in a bit more detail there? Because that'll be about it. Cool. All right. That's about it then. So let me get out the notes and we can shoot into the breakout rooms. This one's week 7. Geez, we're getting through the terms real quick. Week 7 for you guys. So as I said, it's 16A through to 16D. The document is in there in the Word doc if you need to grab a copy of the notes. Otherwise, yeah, let's make some breakout rooms, and I'll be floating around to answer any questions that come up, either about this thing or about whatever else you're currently doing. Now let's see. Yeah, rejoined. 1, 2, 3, 4. That'll do it. All right, have fun. I'll do some rounds. Yo, you still there? He's gone. Oh no. All right, let me just message. Can I message you direct? How do I do that? Input chat. Oh, here we go. Start a new chat. Oh, we did it. As I was typing. All right, cool. Let's do it. Hey, hey. Bit of a revision there. How's it going?
Good.
Was there anything in particular you'd like me to have a look at?
Not really. I'm gonna do chapter 17 if that's okay with you.
Yeah, by all means, for sure. It's no worries
Yeah.
at all, man. Like I get that everyone's doing different things at different stages, and that's why I say you can even ask questions about stuff you're doing ahead of time.
I mean, I've been doing a lot of this in year 10 science because I'm doing the physics.
Yeah, that's good.
Yeah.
Easy. All right, cool. Yeah. If anything comes up, I guess let me know.
The kinematics part of it is pretty easy. Obviously the formula is okay, like you can memorize it, but I've heard it doesn't really come up much, right, in like actual methods.
No. So as soon as you pass Unit 1 and 2, doesn't show up ever again.
Yeah, because then it's just like actual diff and anti-diff.
Yeah, exactly. It's just actual stuff, which you you probably will, because you practice enough. You probably will just remember it anyway. In fact, it might be in the CAS diff by first principles equation. I wonder. Like search into my calculus, derivative at point. I guess that's what derivative at point does, huh? Yeah. Anyway, point is just like you mentioned. There's no real point knowing this until like, as long as you get it up until the sack and you get it good on the sack, you can drop it from there on.
Yeah, cool.
Easy. All right, I'll leave you to it. And I think, yeah, usually when I do one round, I'll probably just hop back into the main room. So if you have questions, I'll be in the main room. So maybe just jump in there. Because instead of me going around a whole bunch of times, I think I do one round and then I'll hop in the main one.
Yeah, cool.
Easy. All right, that's that. Hello. How's it going, Pia?
I'm good. How are you?
I'm doing good. You'd be having, it's this week, right? The sack?
Yeah.
Okay, cool. Any last minute clarifications you want?
Yes. So when you're graphing on the CAS, right?
Mm-hmm.
And then you do a graph trace, is there any way you could make like the coordinates fractions instead of decimals?
Oh no. Yeah, unfortunately not. I would love them to be exact. I would love them to be fractions.
Yeah.
It just doesn't do it. Which is why I'm pretty much always saying you use the graphing stuff purely to get a picture of what's going on, but you do need to be familiar with the CAS solve type stuff to get the exact values. Yeah.
Right.
It's an unfortunate limitation on there. I've looked, and because I would love it, because the graph trace would be super cool. You just have it, you do the thing. You don't have to know any of the math behind it. You just have it. It's there.
Yeah.
But yeah, unfortunately, there is no such feature that I've been able to find. Anyway.
Right.
Anything else you'd like me to have a look at?
There was a question from the chapter 15 chapter review.
Mm-hmm. Chapter 15 chapter review.
Yeah.
Okay, bust it out. I'm just going to pull up the unit 341. Whereabouts?
Question 3, technology free.
Question 3, tech free. Okay, let's have a look. This one is a percentiles. I will just pause for a second because someone did just join. I'm going to put them in a breakout room real quick. Let's put them in 6. Okay. Yeah, so this is where you have a known probability, but you have known probability, you have the function, you have a domain. What you don't have is this C value. So if you think about how you calculate continuous probabilities, the way that works is in fact, I'll let you answer that. How do you normally calculate continuous probabilities, just in general?
You put the domain in the integral and then you antidiff and just sub it in.
Yeah, precisely. So if I said try to solve the probability between 0 and 1, you would put 0 as your lower bound, 1 as your upper bound, and that would give you some probability. Now in this case, we know what the probability is. So instead of me plugging in upper and lower to get probability, I have probability and I need to find upper and lower. That's the swap. Now, x being greater than c, only one of the lower or the upper will be unknown. Do you know which one we have here, lower or upper? Think about number lines as well. So if you have some value c and everything greater than c, would c be a lower bound or an upper bound?
Lower.
Lower bound, exactly. So the way you would solve this is you would have c as your lower bound, pi as your upper bound, because that's given as part of the domain, and you make the integral equal to 0.8. Now you might, in a tech-free way, you antidiff this, right? You do capital F of pi minus capital F of c equals 0.8, and then you try to solve from there. Did you get that far, or was that the issue?
Yeah, that was it.
That's the issue? Okay, cool. So is it fair enough how you continue from then?
Yeah.
Easy. All right. Any quick ones? Or is that about it?
That was about it for now.
Okay, cool. So I'll continue doing the rounds. After I finish the first round, I'm actually going to hop in the main room. So if you have questions further, best off popping back in the main room for there, because I don't usually have time to do a second round afterwards. So I think it's better off if people then come to the main room to ask questions if they still have them, rather than someone missing out. All right, I'll keep going. You enjoy. Hello, hello. How's it going, Shiloh? You've only just been doing these recently.
Yes, I was like, oh, we just did this like last week. Yeah, I'm just going over the homework and the notes that you took. I just wrote them down. And yeah, nothing too heavy right now.
Easy. All right, chill then. Yeah, so nothing you want me to have a look at all?
Not really.
Easy.
Yeah,
That's what I
kind
like
of.
to see. Crushing it. Awesome. I'll continue doing the rounds. I usually only have time to do one round of things though. So what I'm going to do is once I do the first round, I'll hop in the main room. And if you have questions there, just make sure you hop back into the main room to get them answered. Okay?
Oh, okay. All right.
Easy.
Back.
Bye. Hey, you made it. Missed the whole lesson. What's going on? Oh, is he there, or is he just waiting and away from keyboard? Oh no. Maybe he's typing. Uh-oh. Wake up. If you're currently typing something, you can just like control exit to do a quick yes, no if you're here. That way you don't lose your question if you're asking one. Be in main room. You need. Cool. All right. Does anyone else? Tick, 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 tick. Damn, maybe I did go fast.